time. So John is going to continue his story about solving Laplacian systems, and today for directed graphs, so recent work. Go ahead, John.
Yeah, so last week we talked about Laplacian systems of undirected graphs, and this week we're going to talk about solving Laplacian systems for directed graphs. And last week, the talk was, I think, somewhat detailed. This week's talk is going to be a little bit higher level, although we will go into some details at some points in the talk. And so there's three main parts of this talk. First, we're going to talk about fast algorithms for solving directed Laplacian systems, so algorithms that take a small amount of time. Then we're going to talk a little bit about multiplicative approximation for asymmetric matrices, which is an important concept that we use, and it's a generalization of the multiplicative approximation for symmetric matrices that we talked about last time. And then in part 3, we're going to talk about low space algorithms, algorithms that take a very, very small amount of space. So first, fast algorithms. So often in mathematics, some of the most interesting and I think beautiful ideas come from when you can take a mathematical object and view it from a variety of different mathematical perspectives. And I think this is sort of the case for what's the so-called Laplacian paradigm in the field of numerical linear algebra. So the idea is that you have an undirected graph, but you can equivalently view that as either a reversible Markov chain, that's from sort of a random walks perspective, or from a linear algebraic perspective as a Laplacian matrix. An Laplacian matrix it's denoted L, and it's defined as D minus A, where D is the diagonal matrix of out degrees of the nodes in the graph, and A is the adjacency matrix, where by adjacency matrix, we mean the matrix where the columns tell you the neighbors, the column I tells you the neighbors of node I. And also, of course, one of the things about Laplacian matrices is that you can view it as the right-hand side of the heat equation. It's a discretization of the Laplace operator, but we're not really going to talk about that thing so much in this talk. So one of the nice things about this Laplacian paradigm is that it's enabled the discovery of nearly linear time algorithms for a variety of different problems in theoretical computer science. So from the linear algebraic perspective, we know how to, this is all, by the way, for undirected graphs we're talking about right now, remember? We know how to quickly find, for example, the kernel of a Laplacian matrix. That's actually very easy because it's just the all ones vector. It's just something you can sort of see if you write it down. We also know how to solve what are called Laplacian linear systems. That is linear systems where the matrix of the system is a Laplacian matrix, and do a variety of other linear algebraic tasks with Laplacian matrices very quickly. And leveraging these linear algebraic algorithms that run in nearly linear time algorithms for problems in these other two domains have also been found. So for example, if you have a reversible Markov chain, you can quickly find the stationary distribution of that. That, once again, is easy just because if you have a reversible Markov chain, that's a random walk on an undirected graph. You can just write down the stationary distribution. It's proportional to the degrees of the nodes in the graph. You can also do more difficult things like computing hitting times or approximating the mixing time of the graph and various other sort of random walk type expected quantities. And you can find these quantities all in nearly linear time. And then finally, from the combinatorial sort of undirected graph perspective, you can solve problems like approximating max flow, balanced partitioning, computing uniformly random spanning trees of a graph, and various other problems. And so this naturally all raises the question, if this approach has worked so well for finding fast algorithms for undirected graphs, can we do the same for directed graphs and sort of come up with a directed analog of the Laplacian paradigm? So what might that look like? Well, now we'd have a directed graph. Instead of a reversible Markov chain, random walks on directed graphs just correspond to arbitrary Markov chains. And then from a linear algebraic perspective, we would want a directed analog of the Laplacian matrix. And once again, the Laplacian matrix, right, it's written as L, and it's defined as the diagonal matrix of out degrees minus a transpose, right, which is the matrix where the columns of the matrix are the neighborhoods of the nodes. And it's a weighted matrix. And then we can ask all these problems again in a directed setting. So You could, once again, try to find the kernel of these matrices, compute the stationary distribution, which remember were easy in undirected graphs, and everything else that you would potentially want to do. And once again, ask, can we do this in nearly linear time? So in particular, for computing the stationary distribution and finding the kernel of a matrix, which, hello?
Sorry to stop your speeding, but can you just maybe explain again how exactly do you define the directed Laplacian matrix?
Oh yes, sure. So it's denoted as L, script L, and it's defined as the diagonal matrix of out degrees D out minus the transpose of the adjacency matrix, A transpose.
Where the adjacency matrix now is, how is it defined?
So sorry. Yeah, I shouldn't have said the thing about, in the undirected case, I shouldn't have said the things about the columns of the matrix. So here, so you have A transpose, and the columns of A transpose are like the neighborhoods of like the nodes in the graph. About neighborhoods.
Sorry.
So you have, Leo, for this L, on the diagonal, you just have the number, for every vertex, the number of edges going out of it.
Yeah, and in this case, it's a weighted graph, so you should think like total weight.
Or total weight, yeah. And in the ij entry, it's the weight of the, of the edge from I to j, or from j to I, depending on the transport.
But now it's from I to j and from j to I, it's a different edge, right? Or it's so.
Yeah, it's not symmetric. It's not symmetric, exactly. Yeah, but still the sum in L, the sum of rows, I guess, is still 0, like in the undirected Laplacian.
Or it'd be the it'd be the sum of columns, I think, would be 0.
Fine.
But
okay. Yeah, it depends whether you want the uniform vector to be a right eigenvector or left eigenvector.
Okay, thank you.
Mm-hmm. So it turns out that these problems of finding the kernel and stationary distribution, which were very easy in the undirected setting, become harder in the directed setting. And so we'll go into that in a little bit more detail soon. But just to sort of give some flavor, right? Yeah.
So now it means that the uniform vector is the left kernel, and the hard problem is the right kernel.
That's right.
Okay.
Yeah, the left kernel is still easy. That's right. Yeah. So and yeah. So just like right, the reason like why is that before you could just read off the kernel, it's just all one's vector for both sides in the undirected case, but in the directed case now we just don't know what the right kernel is. You're actually going to have to like do something to find it. You can't just write it down. And same thing for the stationary distribution. You can't just read it off. You're going to actually have to do something to like compute it.
But wait a minute, are you assuming here that the underlying graph is connected?
So you probably want to assume that for this talk, because otherwise there's going to be like more than one kernel. I mean, you can if you want to solve these things for like disconnected graphs, you can do that leveraging a solver for connected graphs. But we're not really going to talk about that in this talk.
All right. Thank you.
John, maybe you're going to say that just one structural, big difference between the directed and undirected case. You explained that in the undirected case, it's not only easy to read off the stationary distribution, but the ratio of numbers you get there is just small, is at most the size of the graph. But in a directed case, you could have exponentially big ratio between the entries of the stationary distribution.
Yeah, that's true. I wasn't gonna go into too much about that, but I guess one thing is that everything we're going to talk about today, like you don't want to do it on something with like an exponentially bad stationary distribution, because we're going to pay like a factor that's like logarithmic in like the stationary distribution. So you want like a polynomially poorly conditioned graph.
Okay.
And so for all these problems, at least prior to our work, there were no nearly linear time algorithms known. So the best that was known was that for the problems from the Markov chain and linear algebraic perspectives, you could just solve a linear system to solve these problems using a general purpose linear system solver, which takes matrix multiplication time, or if you want to use something like conjugate gradient, you can do that too. And for these directed graph problems, all of them were worse than linear by a polynomial factor for the best run times. And so what our work does is it solves the problems in the bottom two perspectives, essentially. So solving Markov chain problems on directed graphs and these linear algebraic directed Laplacian matrices in time that's nearly linear in m plus n, where m is the number of edges in the graph and n is the number of vertices in the graph. And then an interesting question for future work is whether, just as in the undirected setting, you could leverage these primitives to get faster combinatorial or faster algorithms for combinatorial problems on undirected graphs. Whether you could leverage now these directed graph primitives to get faster algorithms for these same kinds of combinatorial problems on directed graphs. So now I'm going to talk about how we did what we did. So first, I need to define something called an Eulerian graph. So a directed graph is Eulerian if the weighted in degree of each vertex v equals its weighted out degree. So here we see a vertex v. Its weighted in degree is 1 plus 2 plus 2, which is 5. Its weighted out degree is 3 plus 1 plus 1, which is 5. So the weighted in degree and weighted out degree of v are equal. And if the weighted in and out degree are equal not just for v, but for every vertex in the graph, we call it Eulerian. And we don't require that the number be the same for each vertex. It can be different for each vertex. It's just that it needs to be the same for the in and out degree. So we could have some vertex u, which has like in and out degree 7, and that would be fine. And so one thing that we show is that all of the problems on the last slide that we said we could solve, all of that reduces to solving a directed Laplacian system. So solving a linear system Lx equals b, where L is the Laplacian matrix of an Eulerian graph. So we go from the case of a general graph down to the case of just a graph that is Eulerian. And that's going to be very helpful to us. So then once we can do that, we need to actually be able to solve Lx equals b on Eulerian graphs quickly. So we show we can do that. And then finally, let me see, and then finally, we give one of the primitives that we use in order to be able to solve Lx equals b on Eulerian graphs quickly is what's called a fast sparsification algorithm for Eulerian graphs. And so we'll talk about that as well.
John?
Yeah.
The first theorem again assumes something about a condition number of the graph, or you don't?
Yeah. So when I say quickly, what I mean is like nearly linear time, where the dependence on the condition number or equivalently on the mixing time is at most like logarithmic.
Okay.
And so today, instead of just for simplicity, instead of talking about how to reduce every single thing to solving Lx equals b on Eulerian graphs, we're going to talk about solving just the stationary distribution for Eulerian graphs. And it's like a slightly different algorithm and analysis than what we have in our paper. It's based on personalized PageRank. And yeah, as I said, it's reducing only to finding the stationary distribution, not everything possible, but like the stationary distribution is sort of the most important thing. And from that, you can find pretty much everything else. Okay, so first I'm going to talk about PageRank. So it was invented by the founders of Google, and it was originally used for ranking websites. And here's the definition. So a PageRank random walk with restart probability gamma on a graph G is the random walk obtained as follows. With probability gamma, you jump to a uniformly random vertex, and otherwise you do a standard random walk step in the graph. Then we can define, so we define a PageRank random walk. Now we can define a personalized PageRank random walk. And what that is it's a personalized PageRank random walk with restart probability gamma and starting distribution B on a graph G is the random walk where with probability gamma, you sample a vertex from B and otherwise do a standard random walk step. So the only difference between these two definitions is that instead of jumping to a uniformly random vertex with probability gamma, instead with probability gamma, we jump to a vertex sampled from the distribution B. And then the personalized PageRank can be defined as the stationary distribution S of the personalized PageRank random walk. Okay, so then now that we've defined personalized PageRank, we can define we can give three equivalent definitions that are equivalent to the definition that we've already seen. So first, the original definition that we saw. That's just copied from the last slide. And so if we sort of expand this definition a little bit, let's let W be the original walk matrix of the graph. So this is the walk matrix of the graph, not of the personalized PageRank random walk. Let's let the restart probability from the personalized PageRank random walk be gamma. The starting distribution B that the personalized PageRank random walk uses when it restarts be B. And finally, we'll use X to the I to denote the distribution of the personalized PageRank random walk after I steps. Oh, and the stationary distribution of the personalized PageRank random walk is S. So then we can ask, suppose we do a personalized PageRank random walk, how does the distribution change after each step of the walk? And so it's given by this recurrence. So we get the distribution in the I plus first step of the walk, the personalized PageRank random walk, from saying, all right, with probability gamma, we just take a vertex from the distribution B. That's where we get a gamma B term. Plus, with probability 1 minus gamma, so if we decide not to do that, then we just take a normal random walk step in the original graph. So we multiply W times the previous state, X to the I. That gives you the new distribution that you get after just taking a random walk step according to the transitions in the original graph.
John?
Yeah.
Can you say anything about the intuition of why you would want to do that? Even the usual PageRank, why would you, or the personalized one, why would you ever want to do that? I mean, you could, of course, go to whatever distribution you want, or you could do the random walk. Why do you want to mix them?
Why do you want to what? Sorry?
To mix them. I mean, this is, you take a convex combination of going to a fixed distribution or doing the random walk. Why would you ever, want to take such a combination? What's the intuition?
Oh, instead of just taking just an ordinary random walk on the graph or something?
Yes, yeah. What do you gain intuitively? What's the point of doing this kind of thing?
Yeah, so I think there's sort of two reasons. One is sort of just a very like the reason that it just doesn't so this was originally used for ranking websites, and you use the PageRank of each vertex. So in other words, the probability of each vertex according to this distribution to as a sort of measure of their importance. So things that are better connected to the rest of the graph have higher numbers, and so you might think that they'd be more likely to be relevant to a search query, because this was originally used at Google. And if you don't do this thing where you randomly restart with probability gamma, then if the graph is disconnected, you may not actually explore the entire graph, which is a problem. And so it solves that problem, and then also it acts as sort of, I think, a bit of a regularization type of thing, so that you can't have grossly different numbers between nodes. So I think those are sort of the two main reasons why it was used for regularization, and just the pragmatic reason that you need to explore the entire graph. Yes,
but do you need, this algorithm is also used to update whatever the rank of.
So you can use, so this is I mean, you can use this as this recurrence as an actual algorithm just by iterating this recurrence if you want to. That's true. It's not a very it's not a super fast algorithm. It takes time. It's like 1 over gamma or 1 over gamma squared, a number of iterations. Whereas with our methods, you'd have a logarithmic dependence on 1 over gamma. Is that?
Yeah, it's good. Yeah, thanks. That's good.
but right now, like, we're not thinking of this really as an algorithm, or as just like just a linear recurrence that defines the PageRank. And so the stationary distribution of the personalized PageRank random walk, it's a stationary point of this recurrence. So if we can substitute in s in place of xi and xi plus 1, and that gives us a linear system that we can solve that tells us the personalized PageRank, and the answer is s. And so we can just move things over to the left-hand side to make it sort of more conventionally look like how linear systems are written, right? And then what we get is the thing that multiplies s on the left-hand side is I minus 1 minus gamma w over gamma. That times s is equal to b. And so we call this matrix on the left-hand side p sub gamma. Okay, so now we've seen two definitions of a personalized PageRank random walk: the original definition, and then this new linear system definition that we just wrote down. And then a final definition is what we're going to do on this slide. So once again, we're just copying down the original definition from the last slide as well as 2 slides ago. And so if we sort of think about this definition, what it's saying is that in each step, the personalized PageRank random walk has gamma probability of restarting. And so what that means is that the time between restarts, t, is a geometric variable where the probability of restarting is where the expected number of steps until you restart is 1 over gamma. And the distribution of your current location, remember, only depends on what has happened since the last time you restarted. Because every time you restart, you completely forget your history and just go to some fixed, distribution. And so from this, we conclude the following lemma: the stationary distribution S of a personalized PageRank random walk is equivalently the distribution of a random walker's final position after starting from the distribution B and taking t steps, where t is a geometric variable with expected value 1 over gamma. Okay, so now we're just going to put up a lemma that has these 3 definitions of personalized PageRank that we said, right? So one is it's the stationary distribution of the personalized PageRank random walk with restart probability gamma and starting distribution B. The second is that it's the solution to the linear system P gamma S equals B. Or in other words, you can get it by applying the matrix P gamma inverse to the vector B. And then finally, it's the distribution of a random walker's final position after starting from the distribution B and taking t steps, where t is a geometric variable, random variable, where the mean is 1 over gamma. So now, suppose we have two numbers, gamma 1 and gamma 2, and we want to interpret the quantity p gamma 2 inverse times p gamma 1 inverse b. How can we interpret that quantity? So what it's saying, if we think about it from the third definition's perspective, is that we start at the vector b.
John, do we know that p gamma is invertible, or do we? Or
we do. I didn't argue why, but yes, we do know that p gamma is invertible.
Okay.
Yeah.
That's the gamma shift makes it invertible.
Sorry, what?
Oh, okay.
Yeah, gamma needs to be less than 1, or less than or equal to 1. But that is the case. That will be the case here. So yeah, so now we want to interpret p gamma 2 inverse times p gamma 1 inverse times b. And if we think about that from the perspective of the third definition, and so we can first interpret p gamma 1 inverse b. And so what that is, right, is it's due a geometric random variable of 1 over gamma 1 steps. And then if we think about what the p gamma 2 inverse is doing, right, that's doing another. It's like doing another random walk now, starting from the distribution where the random walk that we got from p gamma 1 inverse b ended, and it's doing it for 1 over gamma 2 steps. So it's really just doing 2 back-to-back random walks of with 2 different numbers of steps. It's really just like doing 1 random walk where you add up the number of steps. So it's you start at b, do an ordinary random walk for 2 steps, where t is the sum of 2 geometric random variables, where the first has expected value 1 over gamma 1, and the second has expected value 1 over gamma 2. And so from this perspective, we can see that, as gamma 1 and gamma 2 go to 0, this converges to the true stationary distribution, which is good to know. And it suggests the following algorithm. So we can start from a starting distribution B, and then compute a very long product, P gamma K inverse times, a bunch of different P gammas all the way down to P gamma 1 inverse times B, and keep on stacking on factors of P gamma inverse for various values of gamma until the result actually does converge, close enough to the stationary distribution, that we're happy with the accuracy. And right, the reason why this works, yeah.
What is the stationary distribution? Isn't that what you're trying to find?
Yeah. So this is an algorithm for doing that.
So,
it's going to have like some problems, but it is a legitimate algorithm for doing it.
No, I'm not sure what does it mean until it converges to a stationary distribution. How do you know that you got to a stationary distribution?
So if you look back on this slide, when you multiply P gamma inverse times a vector, that's definition 3 in the lemma, right? Then what it says is that the result that you get from doing that is equivalent to the distribution of a random walker's final position after starting from the distribution given by the vector and taking t steps where t is a geometric random variable with mean 1 over gamma. And so if we multiply by a large number of these P gamma inverses, then it's like taking a number of steps where the number of steps is a sum of geometric random variables. And if we just do a large enough product where that will make the expected value of the sum very large, and so as the expected value of that sum goes to infinity, the result of the product times the vector will converge to the stationary distribution. Is that?
Stationary of what? Of P gamma?
Stationary distribution of the original graph.
Okay, of W. Like if you had no gamma.
If we what? Sorry.
If you had no gamma.
Yeah, that's right. Or or as equivalent like as gamma goes to 0.
Yeah, it seems like I mean at this point you don't need many gammas. You could just take gamma to go to 0, and even by this definition, one step will be fine. But you have a reason to.
Yeah, that's right. Yeah, the reason why we don't just directly send gamma to 0 is just that. I mean, there is a version of this actually where you could send gamma to 0, but it's not quite as nice to write down as what we're going to talk about today.
Okay.
And morally it's very similar.
Have you used anything having to do with Eulerian property yet?
No, not yet. We really like the Eulerian stuff. The Eulerian stuff is going to become sort of more important a little bit later in the talk, but right now we're not using anything about Eulerianness.
Thank you.
Okay, so if we take a product of P gamma inverses times B, so this is just then like the interpretation of that, just according to the stuff on the previous slide, is you start at B, you do an ordinary random walk for t steps, where t is a geometric random variable, which is now a sum of geometric random variables, where each of the means of the geometric random variables are 1 over gamma I for each gamma, and then you output the result. And so there's a couple of problems with this algorithm as I've written it. So first, you might have to multiply by P gamma inverse, a large number of times. If for example, if gamma is like a half, or sorry, not do I want to say half? Yeah, if it's a half, then that's a problem, because then like each 1 over gamma I term in the sum is just 2, And so if you're like mixing times like n or something, you might have to multiply by like n of these matrices if gamma I is each gamma I is like some like constant fraction. Second, we have to multiply by the inverse of this p gamma matrix, right? We have the p gamma, or each of these p gamma matrices, and we don't necessarily know how to compute these inverses, so that's a bit of a problem. And then finally, this is like a direct algorithm, and we said we wanted to do a reduction to the Eulerian case. And so now we're going to talk about sort of how to solve these problems. Okay, so recall from the previous slide, right? This is the thing that we're sort of trying to compute, right? It's a like product of p gamma inverses for different values of gamma times b. And so if you recall the problems that we said on the previous slide, right? The first problem was that we might have to multiply by p gamma I inverse for many different values of gamma I, potentially like a polynomial number without other assumptions. And so the fix for this is that we make the gamma i's exponentially decreasing. And so if we do that, then the number of p gammas that we're going to need to multiply by now is only going to be logarithmic, which is fine, instead of polynomial. And a second problem is that we may have to multiply by the the inverse of these matrices, which we don't know. And so the fix of this is that if we want to just multiply by the inverse of these matrices, it turns out that it's actually easy to do this, provided that you have an Eulerian Laplacian linear system solver, so we can solve Lx equals b on Eulerian graphs for arbitrary Eulerian graphs, and it provided that we know the suffix of this product all the way up to p inverse of gamma I minus 1. So in other words, if we want to multiply any vector by p gamma I inverse, we can do that given this Eulerian Laplacian system solver, which we haven't said yet how to do, and with knowledge of the vector product of p gamma I minus 1 inverse all the way down to p gamma 1 inverse times b. And yeah. And we're not going to really talk about precisely how to do that, but just something you can do. And then finally, the problem, there's a problem that the algorithm was direct, and now this algorithm is not direct, right? It uses an Eulerian Laplacian system solver, so it is in fact a reduction to the Eulerian case. And so that's really all we're going to say about the reduction. Obviously, there's a big chunk of that, right? I left out, right? How you actually use an Eulerian Laplacian system solver and knowledge of a suffix of that product to actually apply the inverse of these p gamma matrices, but that's sort of a little bit too much to fit in this talk.
But John, I mean, you face this problem even in the first step, right? I mean, forget the suffix. I mean, when you apply the first p gamma 1 to b, you already have this issue. So how is it? I mean, maybe you can say some intuitive word on how applying the inverse, let's say the inverse of the first.
So you don't have this problem in the first step, because in the first step, like since the gammas are exponentially decreasing, you can assume that the first gamma is like a half or something. And in that case, you can just use the naive algorithm of just iterating that recurrence we saw a couple of slides ago. And every time is polynomial in gamma, but since gamma is constant for gamma 1, that's fine.
I see. So it becomes more interesting after a few steps of this, but it's another vector. Yeah. I mean, maybe you can say what properties of the vector you use in order to be able to use the Eulerian solver.
Yeah. So literally the main property is just that the vector is like somewhat close to the stationary distribution and under a very specific notion of distance. I guess maybe I can say a little bit more than that. So if you wanted to, sort of try to naively compute or try to naively take an arbitrary linear system that was of the form like diagonal matrix minus something and turn it into a Laplacian linear system, and you're willing to sort of lose something when you do that, then what you could do is you could scale up the entries in the diagonal matrix to make them larger than the entries in the matrix that you're subtracting off, and then mess around with it a little bit more in order So this will make the diagonal entries bigger than the sums of the off-diagonal entries, and then mess around with it to make them exactly equal. And so if you do this, this is morally the same as adding restart probabilities to each vertex. And the size of the restart probabilities will be related to how much you had to add to the diagonal entries in order to make the diagonal entries greater than the sums of the off diagonal entries, in their row, in each row and column. And so and before you do this this act of making the diagonal entries bigger in order to make them dominate their row and column, you can do a diagonal rescaling on the right hand side of the matrix by a diagonal matrix where the diagonal entries of the matrix that you're rescaling by come from this product of suffix product of the p gamma I minus 1 to the -1 all the way down to p gamma 1 to the -1 times b. And the closer that suffix product is to the stationary distribution, it turns out that the less you need to rescale or add to the diagonal entries, in order to make the diagonal entries dominate their row and column, which means you don't need as large of a restart probability, and that lets you compute things with like a smaller restart probability. I know that's not a very good good explanation since I don't really have slides on this prepared, but hopefully that's at least some additional intuition.
Okay, maybe I'll ask you again at the end, but okay, thanks.
Yeah. Okay, so now we're going to talk about how we actually solve Lx equals b on Eulerian graphs. So the algorithm is an almost linear time algorithm, meaning it depends only logarithmically on things like the number of nodes in the graph, the mixing time or equivalently condition number of the graph, and so on. And so the intuition for this algorithm comes from the Pang-Spielmann 2014 algorithm. So if you remember last time in the talk when we were talking about undirected Laplacian systems, we covered this Pang-Spielmann algorithm. And it was an algorithm for solving linear systems on, where the Laplacian is that of an undirected graph. And so now we're going to talk about sort of how you can take some ideas from this to solve Laplacian systems now on Eulerian graphs. Oh, and I should have mentioned earlier, Eulerian graphs are generalizations of undirected graphs. Although the algorithm is not going to be the same algorithm for a variety of reasons. So here, L sub g is going to denote the directed Laplacian of the graph G. And so here's basically the idea. So we're going to write the Laplacian of G in terms of the Laplacian of G squared. This is similar to what we did last time in the Pang-Spielmann algorithm. And so what this means is that to solve Lg x equals b, you can instead solve Lg squared x prime equals b, and use that as and then transform that into a solution to Lgx equals b. And so if we repeatedly apply this reduction, right, then we can reduce solving Lgx equals b to solving Lg to the k x prime equals b for some large value of k. And then if we make k large enough, it turns out that solving Lg to the k x prime equals b is easy. And so, of course, just like last time, right, the problem with this sort of, first attempt is that doing this requires, writing down powers of g. It's an exact algorithm that is a legitimate algorithm, but it requires writing down powers of g. And of course, I'm not yet saying exactly, what the reduction is from solving Lgx equals b to solving Lg squared x prime equals b. And and writing down powers of g, of course, is an expensive operation. It takes matrix multiplication time, so we don't want to do that because we'd already be blowing our time budget.
Just to understand, when you write g to some power, you mean the matrix to some power, or?
So I mean the walk matrix to some power.
The what?
The walk matrix to some power. So it's in other words, the graph that you get by for simplicity, assume that the graph the out degrees are all 1. So in that case, the weighted out degrees are all 1. We've normalized things that way. So what that means then is that the adjacency matrix of the graph is actually equal to its walk matrix, right? Because an adjacency matrix where you've normalized everything by dividing the degrees of the out edges of each vertex, so that, or sorry, by dividing the weights of each out edge, so that the total outweight of each vertex is 1, right? That is the walk matrix. And so then if you take powers of such a graph, you're just taking powers of the walk matrix.
Okay, thank you.
Yeah, and so we go into, yes. So so we're not going to go into sort of like exactly the details of how we differ from Pang and Spielman on this. I just will say a few notes, which is that so the if you remember anything from last time about the Pang-Spielman algorithm, it sort of heavily relied on using a better recurrence than the naive recurrence that we gave. In particular, this better recurrence that Pang and Spielman used, right? It sort of helps. It's more symmetric than sort of the naive recurrence, and this helps sort of preserve the notions of approximation as you're doing the recurrence, which is very nice and helpful. It turns out that recurrence that Pang and Spielman use does not really preserve things very well. In a directed setting, you actually lose a constant factor when you do things in the recurrence. Potentially, actually, do we even? Yeah, potentially lose a constant factor. And so what we just do is we actually analyze that naive recurrence, which we said you wouldn't want to analyze when we were motivating the Pang-Spielman algorithm, and we do lose a constant factor each time, but then we use a sort of more sophisticated recursion to in order to sort of make what would otherwise be a very large loss throughout the algorithm sort of go away. And we're not going to go into the details of that because it's sort of, once again, something that's a little bit too much for this talk. So now I'm going to talk about the third thing that I mentioned a while ago that we use when we're solving Laplacian linear systems. So I said that an important subroutine that we use in our nearly linear time solver is a fast sparsification algorithm for Eulerian graphs. And we need it for the same reason that the Pang-Spielman algorithm needed it for undirected graphs, because we need to be able to sparsify powers.
Yeah. About the previous, I saw the two previous slides, two previous parts together, the reduction and the solution for Eulerian. Does this have to do anything or somewhat resemble the ideas that Reingold, Trevisan, and Vadan used to try to, I guess, put RL in L, or maybe this will come also to the part on small space. I mean, there is some
You're talking about the de-randomized squaring algorithm for doing undirected connectivity?
No, that's a different one. That's Vadan Rosenman. I know I'm talking about this seems more related to sparsification. No, but I'm asking about the Eulerian stuff. So, but yeah, maybe if it doesn't ring a bell, then it doesn't matter, and I can ask you about this later.
Okay.
It's a paper that was trying to solve RL equals L by trying to maybe imitate the Nissan pseudo-random generator, and they had some kind of a reduction to some sort of Eulerian version of the graph. So if it doesn't ring a bell, I'll ask you later.
All right. Yeah, I will say that this is like this sort of approach of repeatedly squaring the graph and doing sparsified squaring instead of exact squaring. It is definitely related to the de-randomized square in the low space setting, and in fact. And in fact, you can view the de-randomized square sort of as an application of Nissan's pseudo-random generator, although we're not going to talk about that sort of perspective very much today. Okay, so right, a problem with the thing that we wrote down on the last slide, right, was that you needed like the exact version of this, right, needed to write down exact powers of the graph, and as we talked about, sort of last time in the undirected case, the way you fix this is you need some sort of sparsification approach that lets you, very quickly write down, instead of the exact power of the graph, a sparse approximation to the power of the graph in some, appropriate, where by approximation we mean in some, appropriate linear algebraic sense that we haven't defined yet, but we actually are going to talk about sort of more in part 2 of the talk. So just writing that down, right? Everywhere we use powers of g, we're instead going to use sparse graphs that approximate these powers. And this is going to introduce additional error since we're doing things, approximately instead of exactly. Oh yeah, this is what I talked about at the end of the last slide. But we deal with it via a more sophisticated recursion. All right. So what we want is an algorithm that quickly computes sparse approximations of powers of g to the I. And today we're going to talk about the I equals 1 case. I realize this might sound like a bit of a cop-out, right? Since we're not even saying how to approximate the square of a graph. But just like was the case in the undirected setting, where you could sparsify things just given access to a sampling oracle. In other words, just given the ability to sample edges from powers of the graph, which you can do very quickly. In a similar fashion, in the directed setting, with some additional caveats, it also suffices to be able to sample from the square of the graph in order to compute a sparse approximation square, as long as you can sparsify the I equals 1 case. So that's what we're going to do today. So we can define a sparsification procedure. This is a slightly less specific. It's a slightly less rigorous definition than the one we gave in the last talk, right? So a sparsification procedure takes a graph H and outputs a graph H prime, such that H prime is sparse, and the directed Laplacian matrices of H and H prime approximate each other in an appropriate linear algebraic sense that we're going to talk about in a little bit more detail later. And we call H prime a sparsifier of H. And so in undirected graphs, sparsification is sort of quote unquote easy. I say that because it took a long line of work sort of to get there, but now nowadays sort of we do know how to do it fairly easily, right? And what the sort of simplest conceptually algorithm is now is that you just compute a special number for each undirected edge. If you remember anything from last talk, it was something involving like the trace of the inverse of the matrix times something that is in like some sort of sum decomposition of the matrix. And you really approximate this rather than computing it exactly, but you don't need to really remember that. And then we sample a bunch of undirected edges with probability proportional to each of these special numbers. And if we sample enough edges, then we get a good approximation of the graph. And here enough is like if the graph is on n vertices, then it's like n log n over epsilon squared to get epsilon error in whatever notion of error we haven't specified yet. And it's independent, so it's independent of the number of edges in the original graph. It just depends on the number of vertices. In directed graphs, sparsification is harder, and I'm going to try to sort of motivate that a little bit now for why it's harder in directed graphs. So first, you could try to just do the undirected algorithm in directed graphs. So just computing a sampling probability for each now directed edge, and sampling a bunch of directed edges according to each of these probabilities. And hope that if we sample enough directed edges, then the resulting graph will approximate the original graph. And while this is, of course, just true in the limit, due to just the fact that everything will converge if you take enough samples, the number of samples that you need is much higher if you do this. And to sort of see why, let's consider the undirected cycle. So this is an undirected graph, but of course we could try to use this, direct. But the algorithm, right, that we said on the previous slide, it's an algorithm for directed graphs. And undirected graphs, of course, are a type of directed graph. So we would hope that if this algorithm for directed graphs works, it works for undirected graphs as well. But in fact, it doesn't very well. And so so let's say we have some undirected cycle. Then if we do directed edge sampling, we just sample each directed edge with some probability, then we're probably going to end up with different weights in each direction after we do our sampling, just do this sort of natural variation in the sampling process. So maybe like for the edges between U and V, instead of having equal weights in each direction between U and V, maybe we have weight, I don't know, 7 in one direction and 13 in another direction, instead of them being equal after we take our samples. And so here's why that's bad. So you might wonder if it's okay, but it's not, because so first, from a combinatorial perspective, it's sort of different weights in each direction, and in particular like different weights on each side of each vertex, means that it's very unlikely that after we do this, the graph will remain Eulerian. So right, undirected graphs are a type of Eulerian graph, but after we do the sampling process, it will not be undirected and will not even be Eulerian, which you might think is potentially bad. From a random walks perspective, you can show that the stationary distribution of the graph greatly changes by this kind of change in the weights, and it also greatly changes the commute times as well. I'm not going to argue either of those things today, but it's true. And finally, from a linear algebraic perspective, sort of equivalent to what we said from a random walks perspective, the kernel of the matrix can change by a huge amount, and it can be and the resulting directed Laplacian matrix can be a polynomially bad preconditioner of the original matrix. And in the sense of preconditioning, we talked about it in the last slide. It's fine if you don't remember that definition. But so the point is just basically from every different perspective, like the graphs do not approximate each other. So it's very sort of, I think, convincing evidence that this algorithm, this naive attempt at an algorithm doesn't work in the directed setting anymore.
So John, can you say a few words about, I mean, in the previous case, the matrices were diagonalizable, the eigenvalues were real. You actually exploited positive semi-definiteness. In the directed case, can you make sense of an ordering among the matrices to say that you have a sparsification?
Yeah, so you're right. You don't have like this kind of like nice ordering on the matrices that you have anymore in the directed setting. We're going to talk a little bit more about sort of like how like some of the stuff that you talked about like maps over to the directed setting in terms of like what matrix approximation means in the directed setting in part 2. For now, I'm just sort of black boxing that.
All right, thank you.
Okay, so oh, and right, just a quick note. So each of the things I just bolded, that it's no longer Eulerian, that the stationary distribution greatly changes, and that the kernel of L changes a lot. All of those three things are sort of actually like equivalent phenomena. Just because, right, like the kernel of L like actually is the stationary distribution. If the adjacency matrix is the walk matrix, so these things are equivalent. And so that's just sort of the following key idea. Since the lack of Eulerianness seemed to be like the cause of problems in each, from each of the perspectives we looked at the graph at, and that's just explicitly to preserve Eulerianness. So now in a second attempt at an algorithm, what we can do is we can randomly sample directed edges like we did before. But now after we do that, we can do a patching step where we add additional edges to the graph in order to force it to be Eulerian. And so there's problems with this. So first, we still don't know what probabilities to sample with, in order to make the number of, edges we need to sample, not huge. And second, this patching procedure that we do, if we're just arbitrarily adding edges to a graph to force it to be Eulerian, we might be adding edges, over, that connect vertices that were previously, very far away in the graph that make them closer. And intuitively, you think that would, add a lot of error. And in fact, it does if you're just adding edges arbitrarily to the graph. So even though, we are now explicitly preserving like, the kernel of the graph and the fact that it's Eulerian, we may be still, it still may not be a good approximation of the original graph, even though it's also an Eulerian graph. And so that's sort of the second key idea, where the second key idea comes in. It's to only sparsify expanders. So what I mean by that is, so you have these problems with the second attempt that we didn't know what probabilities to sample with, and that the sampling procedure could add too much error. But it turns out that if the graph is an Eulerian expander, so just for now, forget the original graph and just assume that whatever we're sparsifying is an Eulerian expander, then you can pretty much sample uniformly. I say pretty much, really, it's like related to like actually like the degrees of things. But if you assume like all the degrees are like 1, then it's basically uniform sampling. And then second, this problem of that patching could add too much error. Well, it turns out that if the graph is an expander, then pretty much any reasonable patching scheme that you could possibly imagine will only add a small amount of error relative to the graph. So that's good. We can sparsify Eulerian expanders. And so that leads to the following third attempt at an algorithm. So first, we now do an expander decomposition, decomposing the graph into a bunch of Eulerian expanders. And then within each of these expanders, we uniformly sample directed edges and do patching, again, just within each expander separately. So we patch the expander separately to separately keep each of the expanders Eulerian, and if we're separately keeping each part of the graph Eulerian, this makes the entire graph Eulerian overall. Unfortunately, this algorithm still doesn't quite work because we can't always decompose an Eulerian directed graph into Eulerian expanders. So like just an example of this is if you have a like directed cycle, then you can't decompose that into like small Eulerian expanders, just because if you take if you try to decompose it at all, you'll get non-Eulerian things that are, in fact, they're not even strongly connected. Okay, so that brings in our final third key idea. To instead of doing an Eulerian expander decomposition, to do an undirected expander decomposition. So what we show is that instead of using actual expanders, it suffices when we decompose the graph into pieces and then sparsify each piece separately and do patching on each piece. We instead instead suffices to use graphs that would become expanders if one erases the directions on all edges. So here we have an example of just a directed path of length 1. So this is not an expander; it's not even connected. But if we erase the directions on this edge, it just becomes an undirected path of length 1, and that is an expander. And so if we decompose the graph into graphs like this, it turns out that the patching and random sampling actually still works. And so that gives us the actual final algorithm. So we do an undirected expander decomposition. I'm decomposing the graph into subgraphs that would be expanders if we erased edge directions. And then within each subgraph, uniformly sample directed edges. And then finally, within each subgraph, patch the graph so that it stays Eulerian. And since each subgraph is Eulerian, the whole graph is Eulerian. And
yeah, complexity of the first step. I mean, it looks like this itself is a non-trivial.
Yeah, it is. Right. It is non-trivial. There's prior work that does this. Because it's an undirected graph problem. And so that's what we're relying on. But yes, it certainly does take work to do this, even in the undirected setting.
And the graph is already sparsified when you do. What's the input model for this step 1?
So no, step 1, the graph is not sparsified. It's just an arbitrary graph. And so you give that.
I see.
Yeah.
It could be done in quasi-linear time already.
It's known how to do this in nearly linear time already. Yes.
Okay. Probably using, I assume it's using some of the previous work on, or it doesn't.
So definitely some of the algorithms for this do use Laplacian solvers. I don't know if they're strictly required or if you can get away without using them, but yes.
Okay, thanks.
Okay, so now we're going to get to part 2 of the talk, which is multiplicative approximation for asymmetric matrices. So, in the previous section, we talked about, sparsifying directed Laplacian matrices, and that we wanted, right, to produce graphs that a graph that approximates some original graph under some appropriate, linear algebraic notions. So now we're going to talk about it in a little bit more concrete detail, like what those notions actually are.
John.
Yeah.
Yeah, just another comment. So last time a couple of people asked me, and I mean, it seems like the start of the second part may be a good time for like a 5-minute break, which you didn't.
Oh, sure, yeah, sure.
All right. So yeah, John, please continue.
All right, yeah. So now we're going to talk about in more detail what it actually means for asymmetric matrices to approximate each other multiplicatively. And so we're going to start out by reviewing sort of what we talked about last time, approximation for symmetric matrices. So if you remember, there's this thing called the Lohner ordering, which is sort of a very natural ordering on positive semi-definite matrices. And what it says, right, is that, or what it's defined as is we define A greater than or equal to 0 if A is positive semi-definite, and A greater than or equal to C whenever A minus C is positive semi-definite. And so this has pretty much, most of the nice properties that you would hope of an ordering on matrices. And so in particular, it sort of implies a very natural definition of multiplicative approximation, analogous to multiplicative approximation for positive numbers. So, right, we can say that A gamma multiplicatively approximates C if A is between gamma C and gamma inverse C. Or, we can just sort of more colloquially say C and A are within a gamma factor of each other. And what we said last time is that there's this theorem that says that if we do have A and C that approximate each other within a gamma factor, then if we want to solve AX equals B, then instead we can solve CX prime equals B prime for various values of B prime, gamma squared times approximately. And this will allow us to solve the original linear system AX equals B. So we can reduce solving AX equals B to solving CX equals B up to like a loss of a gamma squared factor in the number of linear system solves that you want to do. And that was a useful fact that we used last time. And so here it's gamma squared, if you remember, because just we have one factor of gamma on each side of A. And so those end up combining, and that's where you get the gamma squared from instead of just gamma. And so this notion of multiplicative approximation, in addition to this nice property that it lets you reduce solving a linear system with one matrix to a linear system in another matrix, it has some other useful properties too that we talked about last time. So suppose we have A and C that are within a gamma factor of each other, and then also we have N and M, and those are within a gamma factor of each other. So what does that imply? So first, you can add the notion of approximation. So we get A plus N and C plus M are within a gamma factor of each other. This is just a straightforward generalization of the fact that if we have non-negative just numbers, so scalars, not matrices, right? And if we add them up, it a multiplicative approximation is preserved. And then we can also multiply, and that preserves the approximation as long as the multiplication that we do is a symmetric multiplication. So we multiply by the transpose of a matrix on one side and then the matrix itself on the other side. And once again, this is analogous to the fact that if we have non-negative numbers and we multiply through by a scalar, this preserves multiplicative approximation. The only thing is that we have to do it here symmetrically because we're working with sort of a symmetric notion of approximation. And then finally, taking inverses also preserves multiplicative approximation. And once again, this is analogous to what happens with non-negative numbers. That if you have two non-negative numbers that multiplicatively approximate each other, their reciprocals also multiplicatively approximate each other. Oh, and then finally, we have transitivity. So where the gammas multiply. So if we have A approximates B within a gamma factor and B approximates C within a gamma factor, then A approximates C within a gamma squared factor. And once again, this is a straightforward generalization of the property for of transitivity for approximation, multiplicative approximation of non-negative numbers. So now we're going to talk about multiplicative approximation for complex numbers. And the reason that we're going to do that is because so if you sort of unpack what was going on this slide, right, about positive semi-definite matrices approximating each other, sort of ultimately what this comes down to is the fact that positive semi-definite matrices have non-negative eigenvalues, and everything that we're sort of doing ends up sort of mapping onto the eigenvalues, and then ends up becoming a question about how well non-negative numbers approximate each other. And that's sort of the core reason why a lot of these nice properties that hold for non-negative numbers also hold for positive semi-definite matrices. But the problem is that with asymmetric matrices now, even if the matrices are real, they may have complex eigenvalues. And so what that sort of suggests is that if we want to have some reasonable notion of multiplicative approximation for asymmetric matrices, then what we should really start with is trying to get a reasonable notion of multiplicative approximation for complex numbers. And so we're going to sort of motivate that as follows. So complex numbers, you can think of them as two-dimensional vectors within the complex plane, right, where the first coordinate is like the real part, and the second coordinate is the imaginary part. And so one question you could ask is, all right, like, well, how do we define multiplicative approximation? Well, one thing I guess you could, hope for is maybe to define it as just entry-wise multiplicative approximation. So just saying that, the real part of the numbers and the imaginary parts of the numbers, respectively approximate each other within some factor, and that's your definition of multiplicative approximation. But that definition doesn't quite work, because let's consider the vectors 1, 1, and 1, 2, right? That you would get from the complex numbers 1 plus 1i and 1 plus 2i. So these vectors under like an entry-wise vector definition of approximation, these things approximate each other within a factor of 2, since their entries respectively approximate each other within a factor of 2. But now suppose that we rotate them so that one of the vectors has a 0 entry. So if we do that, then after we do the rotation, they're no longer going to approximate each other with any constant factor, since 0 doesn't approximate anything within a constant factor except 0. So what this means is that doing a rotation actually changed whether or not these things approximate each other at all within any constant factor. And so that's kind of bad, especially for complex numbers, right? Complex numbers, like you'd hope that like whatever you do is sort of with them is geometric and is not affected by like rotations, at least intuitively. And so that really suggests that like doing some sort of entry-wise thing is not the right way to go here.
Like
so instead,
coordinates would be better.
What?
Like polar coordinates would be better.
That is not actually the route that we end up taking, but certainly that would be like, if you could make something involving polar coordinates work, that would be nice. We do know of something that sort of is kind of like polar coordinates, although it's still not exactly that, but that we're not going to talk about that in this talk.
Okay, and just a general question: mathematicians didn't consider this in the 100 years ago?
Not that we know of, although it's possible we just may not know of it, but not as far as we know.
Yeah, it's just extremely natural question, right? So,
yeah.
Okay.
I mean, is there anything wrong with using the 2x2 matrix representation of complex numbers?
So like, then I guess you have, well, it's sort of a chicken and the egg problem, right? Because the reason we're doing this is to try to find a way of talking about matrices approximating each other. But if you reduce, complex numbers to 2x2 matrices, then you have to define, what it means for 2x2 matrices to approximate each other. So then you're sort of back at the same problem you started with.
Yeah, but at least polar coordinates exist for matrices as well, right? I mean,
that is true, but again, that's not like sort of the route we're going today. But
okay, yeah, okay,
yeah. Oh, I should mention that one thing that was known previously about this sort of kind of thing was so if you remember last time we talked about preconditioned Richardson iteration, yeah. And so in there, like when we did that analysis, very little in the analysis actually depended on the matrices being symmetric or PSD. In fact, everything up through writing we ended up writing down the norm of I minus this product of a matrix times an inverse norm of that. So everything up through there did not depend on the matrices being symmetric. And so if you have bounds on that quantity, that is one notion of approximation. Although the notions we're going to talk about today are stronger than that.
Okay.
So specifically, so we're talking about, remember, vectors right now in Rn, U, and V. And we say that U and V weakly approximate each other within a factor of 1 plus epsilon if the norm of U minus V is less than or equal to epsilon times the norm of V. So this is a fairly reasonable definition for vectors approximating each other. It's commonly used as a guarantee actually for linear system solvers. So you might so often if you write some theorem that says we can solve linear systems quickly, to error epsilon in time, something depending on epsilon, then this kind of thing will often be your definition of error. Oh, and the norm here, we haven't said a norm. You'd want to pick the norm appropriately to be something that you can actually achieve, although we're not going to talk about exactly what the norm is today. So then, using this correspondence between vectors and complex numbers, you can map this definition over to a definition of approximation for vectors. And if you do that, right, so now we'd say that two complex numbers, A and B, weakly approximate each other within a factor of 1 plus epsilon if the absolute value of the difference of the complex numbers is less than or equal to epsilon times the magnitude of B. Oh, and I should mention this definition, right, as stated, is not symmetric with respect to U and V or A and B, but it turns out even though it's not exactly symmetric, it is approximately symmetric in the sense that you can switch A and B in the definition if you're willing to lose an additive epsilon squared in your error, which is negligible as long as your epsilon is reasonably small. So in practice, effectively, these definitions are equal, at least in all the situations where you'd symmetric, at least in all the situations where you'd actually want to use them. All right, and then so this definition is a reasonable definition of approximation for complex numbers. In particular, it already has several properties that we liked about our definition of approximation for of multiplicative approximation for non-negative numbers. So, for example, if we invert A and B, you can argue that they'll in other words, take their reciprocals. You can argue that they'll still approximate each other if you have approximation under this definition. Also, if we multiply through by both A and B by some complex number, then if they approximate each other multiplicatively before, they'll multiplicatively approximate each other after you do the multiplication. So that's nice. The one thing that's not nice about this definition, though, is that it doesn't it's not preserved under addition. So if we have two pairs of two different approximation equations, A approximates B and C approximates D or something, we can't add up those two approximation statements to get like A plus C approximates B plus D. And that's kind of unfortunate because there's a lot of places actually where we really do want to be able to add up approximation statements and get an approximation statement as the result. Because if you remember the last talk, we had Laplacian matrices that were decomposed into like sums of their edges, and we'd like to be able to talk about like those various decompositions of Laplacian matrices, approximating each other in the directed setting. Like we need to do that in a lot of places. So we really do need like some sort of notion of approximation that lets you add approximation statements. And so now we're going to define a strong approximation, which is a stronger notion of approximation for complex numbers, which does have all of these nice properties that we've talked about so far, and it lets you add approximation statements. And so what that definition is as follows. So once again, we're going to let A and B be complex numbers. And then we're going to say A strongly approximates B within a 1 plus epsilon factor if the absolute value of A minus B, so that's the same left-hand side, is less than or equal to the real part of B. So the real part of B is always no larger than the magnitude of B. So this is a stronger definition of approximation. But because the real part of B is a linear function of B, you can add up these approximation statements, and it implies an approximation statement when you do, because you can use the triangle inequality on the left-hand side and the right-hand side is linear.
But you've lost the invariance under notation.
So yes, that's a good point. I'm glad you mentioned that. So it would seem that way, but actually, if you write it the right way, you don't lose the invariance under rotation. So specifically, let's write down the definition of strong approximation. So the absolute value of A minus B is less than or equal to epsilon times the real part of A. Oh, that should be a B, but whatever. As I said, it's basically equivalent. So the vector representation of this, right, is we take a complex number and write it as a vector where it's real part comma imaginary part. And so if we do that, we can write it in sort of a vector form as the norm of u minus v times epsilon times the first component of v, right? Because the first component of v is the real part under this mapping of complex numbers to vectors. And so right, you can write that as the vector 1, 0 dotted with the vector v. So that's a vector way of writing down this. And so if we rotate all of the vectors, including 1, 0, this preserves the definition under rotation. So essentially, we are privileging a direction, but as long as we rotate everything, it's preserved. And that was not a property that entry-wise vector approximation had. Because in that case, you're actually privileging an entire base. It's not just a single direction. Okay, so now these things generalize to matrices in a fairly nice way. So now we're going to define a weak approximation for matrices. So we have two matrices A, comma B. They're real matrices, real n by n matrices, and we say that A weakly approximates B within a 1 plus epsilon factor if for all x, the vectors ax and bx weakly approximate each other within a 1 plus epsilon factor. So if you remember on the previous slide, right, we had in the bottom left corner a definition of weak approximation for vectors, just saying that their difference, u minus v, is less than or equal to epsilon times the magnitude of v. And so here we're just saying that in that sense, these vectors ax and bx need to 1 plus epsilon multiplicatively approximate each other for all x. And that's weak approximation for matrices. And I should mention this definition of weak approximation is essentially the the definition sort of naturally comes out of what you need for Richardson iteration to work. So in that sense, like that you can sort of think as sort of like a prior work kind of thing. But of course, it has a problem, just like in the vector setting on the previous slide, that this definition for matrices does not add either. You can't add these approximation statements. So we work with a stronger definition, which does add. That should be let A comma B in R to the n by n, not in C. And And so then we say that A and B strongly approximate each other within a 1 plus epsilon factor if for all complex vectors x. So it's very important that here that the vectors, we allow them to be complex. In the previous definition, it doesn't really matter whether you let the vectors be real or complex, the definition's equivalent. But here it is important that it's complex. And so we require that the complex numbers, x conjugate transpose ax, multiplicatively approximate the complex number x conjugate transpose bx for all values of x. So essentially, we're requiring that the complex quadratic forms of complex valued quadratic forms of these matrices multiplicatively approximate each other for all inputs in the sense of approximation, multiplicative approximation for complex numbers that we defined on the previous slide. And there's a slight caveat on this, which is that this definition, like it's within it turns out it's within a factor of 2 of the definition that we actually use in our papers. I don't know if you can actually do the analysis the entire way using this definition, or whether there's some issue like with the factor of 2 difference. But morally, this is sort of what's going on. So that's essentially the definition of multiplicative approximation for matrices that I use. And so the point is that basically it's motivated by defining multiplicative approximation for complex numbers.
Can you say, before you go on, can you say, so this is the second definition.
Yeah.
Really only depends on sort of as you said, the Hermitian form given by A and B, which will have.
It's actually, so that this is why you need to make sure that x is complex valued. If you don't require that x is complex valued, then you're sort of ignoring the asymmetricness of the matrices. But sorry, go on with your question.
I guess I was curious if this matches up with the eigenvalue definition, the sort of generalized eigenvalue definition you had before, but for like the Hermitian, like the average of A and its conjugate transpose. If there's a way to match up
so the average of A and its conjugate transpose is a Hermitian matrix, and so it would kind of be problematic if this definition only matched up with that, because we'd be ignoring the asymmetric structure in A. And it is true that the definitions will match up if x is just like a vector from R to the n instead of C to the n, which is why we need to require that x be a complex vector.
Okay, thanks.
Is that I can if x is a real vector, then you can take the transpose of both these equations and add them, and it's equivalent because the transpose of a scalar, right, is just itself. So what that says actually is that if x is real valued, then this statement is just equivalent to saying that the symmetrizations that you get by just taking the average of the matrix with its transpose approximate each other.
I guess I would. Okay.
And you can't do that if x is complex valued, but and it's a good thing that you can't, because if you could, it would just reduce down to a much weaker statement, which would probably not be usable to do things.
Okay.
So for this kind of definition, matrix, matrix inequalities like matrix Chebyshev or matrix Chernoff-Hall for this type of proximity measures?
Sorry, what?
If you try to get analogs of the matrix inequalities like matrix Chebyshev or matrix Chernoff,
so you can essentially pull this definition or something at least that's equivalent to it within a factor of 2 out of the statements of matrix Chernoff for symmetric matrices. If you apply so you can you can apply matrix Chernoff for symmetric matrices actually to get concentration results about asymmetric matrices. Basically what you do is you just
you symmetrize, you double the
yeah. And so if
it relates to this definition.
Yeah, so if you do that, apply matrix Chernoff for the matrix Chernoff, it's defined for symmetric matrices to get results about asymmetric matrices, and then like write down like what the concentration guarantee you get is, and like what sense of approximation that is, then and sort of expand it out a bit. Then what you'll get is actually it's not quite this, but it is something that's like equivalent up to this within a factor of 2, and that's actually the definition that we actually use, like in the papers. I see. So you could have potentially used also symmetrizing A and B and demanding what you demand for undirected. Well, I guess you have to be careful when you say symmetrize. When I symmetrize, I mean something like you make like a block. Dimension. Yeah, you double the dimension. Not yeah. You double the dimension. Yeah, I guess there's like right when you say symmetrize, there's 2 different types of things you can write. One is that you just like take A plus A transpose over 2 or something. Yeah. And then the other thing is that you like double the dimension and like stick like A's in like the corners, like an A in one corner and A transpose in the other corner. And so right, these 2 things are very different. The first one like destroys a lot of the structure. The second one preserves everything. And so it's the second one, yeah, that we're talking about. Like where you double the dimension. So you didn't have to define the complex versions if you move to this, double dimension symmetrized version? That's right. I mean, sort of like the doubling of dimension is sort of like, I think implicitly like you can represent complex numbers with real numbers as long as you're willing to go up a dimension. I think it's sort of a phenomenon similar to that. Although I haven't actually I don't know if there's like a formal equivalence. Okay. Sort of like complexification, I think, of a vector space is they call it. Yeah. So that's multiplicative approximation for matrices. All right, so now we're going to talk about low space algorithms for solving directed Laplacian systems. And I want to start out by talking about the RL versus L problem, which is a problem about what can be computed in a small amount of space. And when we talk about computing things in a small amount of space, we need to be a little bit careful when we define the model, because if we just sort of naively define things, you can end up with a situation where the amount of space you need is just the max of the input size and output size, since you have to read the you have to write the input somewhere and you have to write the output somewhere. And so to avoid this problem where just the space usage is always just however much space the input or output takes, we define things in a different way where we just ignore the input and output space. So we assume we have a read-only input. We then have an algorithm M, which has read-write memory. It has S bits of read-write memory, and that's actually what we define as the space usage of the algorithm. And then it writes to a write-only output tape the result of the algorithm. And again, we are only charging for the read-write memory that it uses, not for the read-only input memory or write-only output memory that the algorithm uses. Then we can define RL and L. RL is the class of problems that can be computed in this model in logarithmic space when you have access to random bits, and we're not allowed to have false positives, only potentially false negatives. And then L are the problems that can be computed in a logarithmic space in this model where you're not allowed any randomness at all. And sort of a natural question in complexity theory is whether RL and L are in fact equal or different. So whether whether these random bits that you get actually help you compute more problems than you could otherwise in logarithmic space. And of course, an easier goal is, instead of proving RL and L are exactly equal, to try and prove that they're approximately equal up to like sub-logarithmic factors, and even that's not known. That the best that's known is that they're equivalent up to a factor of square root log n. And so this task of trying to show that you can do things with random bits without random bits, it's called de-randomization. There's been several approaches to RL versus L that have been, or trying to get closer to RL versus L that have been studied in the past. One approach is pseudorandom generators. So the idea is that a pseudorandom generator is defined as an algorithm which takes as input a truly random number called a seed, and outputs the seed is generally something you should think of as like a short string of numbers, and it outputs a much longer string of numbers, which is called pseudorandom, meaning that it appears to an algorithm as if it were a truly random sequence of bits, and then an algorithm can't really tell the difference. And so the idea is you can use this to de-randomize a randomized algorithm as follows. So suppose you have some randomized algorithm that takes as input. It's supposed to take as input actually random bits, but instead of giving it actually random bits, you give it these pseudo-random bits from a pseudo-random generator. So if we do this right, the algorithm now is using a smaller number of random bits than it did previously, because now instead of needing to generate every single random bit the algorithm asks for, instead we just generate a small seed using truly random bits, and then use the pseudo-random generator to expand that to a longer string of pseudo-random bits, which the algorithm can then use. And so this reduces the number of random bits that an algorithm uses. But for de-randomization, we want to completely eliminate the random bits altogether. And what's nice about this approach is that, though, as long as the truly random seed that you're using is short enough, then you can just enumerate every possible seed. And since there's no false positives, if the algorithm outputs yes for any of those seeds, you know that the algorithm. So the point is that you can enumerate the seeds. And because the algorithm has no false positives, you can just check whether for any of these seeds that the randomized algorithm would output yes. And if it does, you output yes. If it doesn't, you output no. And this will give you a deterministically correct algorithm for solving the problem. And so now you have a deterministic algorithm, and you've completely de-randomized the algorithm, and you're done. Of course, the important thing, right, is if you still need to be able to do this pseudo-random generation in low space in order for this to work. And so that's really where sort of all the work has been, trying to get the seed length down to a small enough number of bits so that you can actually enumerate it in all the seeds in a small amount of space. And so a Nissan generator is probably the most famous pseudo-random generator. So, and also is is essentially optimal, or at least among what's known so far. You'd hope to do better than it. So it has a seed length of log squared n. So in other words, if n is the number of pseudo-random bits that you ultimately want to generate, then the seed that you need has to be log squared n in length. And that's kind of bad if you think about it, because if you want to enumerate all these seeds, of course you need to be able to write them down. And so the amount of space that you need to enumerate all these seeds is definitely going to be at least log squared n. Just to maintain which seed you're currently enumerating. And we want log n space, not log squared n space. So already sort of with this you're using too much space. But nonetheless, actually, if you do sort of a more complicated analysis, a white box analysis of Nissan's generator, you can actually show that RL is contained in L to the 3 halves. So anything that you can do in randomized space log n, you can do in deterministic space log to the 3 halves n, which is kind of interesting. And so the pros of this pseudo-random number generator approach are that it's oblivious to the input. We just need to define the pseudo-random number generator. It doesn't actually care about what the input to the algorithm is. It just generates a pseudo-random number. It just generates pseudo-random bits, which is kind of mathematically elegant, at least. Pseudo-random number generators also have other applications outside of RL versus L, for example, like in the streaming setting. And pseudo-random number generators also finally estimate the state probabilities at all times. So what I mean by that is that if you use a pseudo-random number generator to de-randomize an algorithm, it's not just telling you whether the algorithm outputs yes or no. You can actually use it to estimate the probability that the randomized algorithm is in a certain state at a certain time for any time that you want in any state that you want. So it's giving you something actually a little bit stronger than just de-randomizing the algorithm. The main cons of pseudo-random number generators really are just that we don't have ones that use a small enough seed length. So we want something like log n seed length. That's what would get you RL equals L, or RL nearly equals L. But we only know how to get a seed length like that in a variety of different special cases. And so that takes us to our second approach of how you can potentially try to solve RL versus L, which is via graph algorithms. And so the idea for this is that it uses the correspondence between randomized algorithms and random walks on directed graphs, which is as follows. So we can view each state that a randomized algorithm could possibly take as being a node in a graph. And then the transitions between states that the randomized algorithm can make, we can represent those with directed edges. And then if we run the randomized algorithm, this is equivalent to just taking a random walk on this corresponding directed graph that we've just defined. And then, we can ask sort of as a, right. So then, if you want to actually like de-randomize a randomized algorithm, you would just want to compute, what is the probability that we end up in the accepting state at a certain time. And if, it's more than two-thirds, then you output yes. And if it's, sorry, this is RL, so it's one-sided error. So if you can end up in it at all, you output yes. And, if you cannot end up in it, then you output no. But this sort of naturally raises the question of, more generally, what we can compute about random walks in deterministic log space is sort of a warm-up to trying to actually, de-randomize algorithms. So what's known is that you can solve ST connectivity in undirected graphs in deterministic logarithmic space. That's a result of Reingold. Like I said, it's in undirected graphs. And a little bit later, it was shown that in not just undirected graphs, but in Eulerian directed graphs, you can also solve ST connectivity in directed space. So this is kind of interesting, right? It's another example of where Eulerian is actually helpful. And in the same paper where Reingold, Trevisan, and Vaden showed that you could solve ST connectivity in Eulerian directed graphs, what they also showed was that if you could generalize this to work not just in Eulerian directed graphs, but in all polynomial mixing directed graphs, including non-Eulerian ones, then you could actually solve randomized algorithms, randomized log space algorithms in deterministic log space. So in other words, it's a complete problem for RL. And it's just via this fact I mentioned earlier, essentially, with some reduction stuff to make like the graph like polynomially mixing, that you just want to check whether you can reach the accept state. Okay, so the pros of the graph algorithm approach are that it gives de-randomization for a variety of natural problems, like these connectivity problems in graphs that we mentioned, for example. The cons, though, are that it sort of only knows how to estimate the long-term behavior of random walks. So, for example, in the above, right, it's sort of only telling you, whether the graphs are connected at all, but not like in the pseudo-random number generator case of like letting you estimate the exact, or approximate probabilities of being in any particular state at any given time. It's only telling you sort of long-term what happens. And so what our work does is it sort of eliminates or helps to eliminate this con. So, and it expands the set of problems that are computable in deterministic, roughly logarithmic space. And so now we actually can compute finite length random walk probabilities. I should mention in Eulerian graphs, hitting times and commute times and escape probabilities. And that says it's all for random walks in both undirected graphs as well as more generally Eulerian graphs, which was not known previously. And I had something about, I guess I should just mention. Whereas like, and so in particular, the thing about like finite length random walk probabilities is it's not a long-term like property of the random walk. It's actually this is a finite length property of the random walk. So conceptually, I think it's like sort of a useful step. And the way that we do this is basically we solve Lx equals b in logarithmic space, where L is the Laplacian matrix of an Eulerian graph.
John, if you can solve these problems, in particular hitting times, why didn't you solve RL already?
It's only Eulerian directed graphs that this works.
But Eulerian is you have it for Eulerian, but not but Eulerian. I see. So you extend the RTV result by computing these numbers on Eulerian graphs rather than just reachability.
Yeah. So it's not just long-term behavior. We can like actually like estimate like this kind of like intermediate behavior as well now.
Okay. Yeah.
Yeah. So I think there's like a useful parallel to draw between sort of the line of work in the low space setting and the line of work in the nearly linear time setting. So specifically, if you recall, like from the first part of the talk, we have nearly linear time randomized algorithms, for solving Lx equals b on undirected graphs, right? This is there's prior work that does it in undirected graphs. So we do it for Eulerian directed graphs, and then give a reduction to the Eulerian case. And then, in the nearly log space deterministic setting, right? So it's known, right, how to solve Lx equals b in undirected graphs. That was a work of Murtaugh, Rao, Sidford, and Vadhan. Or sorry, not Rao, Reingold. Murtaugh, Reingold, Sidford, and Vadhan. And then we generalized it to work in arbitrary Eulerian directed graphs. And then if you could generalize this further to work in arbitrary polynomial mixing time directed graphs, or equivalently, to have a reduction to the Eulerian case, kind of like what we had, in the nearly linear time setting, then you'd be done. You'd have, RL equals L, or at least RL nearly equals L. And that would be really nice. So yeah, it's like sort of all you need is just this reduction to the Eulerian case, and you'd be done. And there's reason to think you might be able to get it because of the fact that it exists in the low time setting, although we don't know how to do it. Okay, so I should mention, right, that if you want to solve Lx equals b, right, this is equivalent actually to just in the low time setting, or sorry, in the low time setting, there's a complexity difference potentially, right, between solving a linear system and computing the inverse of a matrix. It's easier to solve a linear system potentially than to compute the inverse of a matrix. In the low space setting, this distinction difference doesn't really exist. If you can, quickly apply the inverse of a if you can quickly solve the linear system, then you can quickly compute the inverse of the matrix of the linear system. So today we're going to talk about sort of how do you compute L pseudo inverse in low space. And one, application of what we do is deterministic algorithms for solving for estimating to high accuracy the random walk probabilities in Eulerian graphs. And so what this problem is, so like we're going to talk about this application before we actually talk about like how we solve Eulerian Laplacian system, just sort of as a motivation. So we're given a random walk matrix W and some number k, that's a natural number, and an epsilon. And what we want to do is we want to compute W to the k to within entry-wise error plus or minus epsilon. So this is the entry-wise walk probabilities problem. And in particular, we're interested in having like very small dependence on epsilon. So like think like logarithmic dependence on epsilon instead of like inverse polynomial dependence on epsilon. And so what we show is that you can solve this problem in space that is logarithmic in n and k, and doubly logarithmic in, sorry, when I said small dependence on epsilon, I should have said doubly logarithmic dependence on epsilon, right? Because when we think of like small in the time setting, it's like logarithmic dependence. When we think of small in the space setting, it's like doubly logarithmic dependence. So the space usage is basically log nk times some log that depends on nk and 1 over epsilon. And we do it for undirected graphs and Eulerian directed graphs. Okay, so again, we want to do a high precision estimate of W to the k for all k. And the way that we're going to do that is we're going to use a reduction that we have in our paper that we're going to talk about in a minute that obtains that estimate from a high precision estimate of L pseudo inverse, where it's going to be I minus W pseudo inverse, but for a different specially constructed W that lets us read off the W to the k values, which we'll talk about more in a minute. And then we're going to get that high precision estimate of L pseudo inverse from a low precision estimate of L pseudo inverse using preconditioned Richardson iteration. It's essentially the same algorithm that we talked about in the last talk, but adapted for a low space setting. And then we're going to get that low precision estimate of L pseudo inverse from low precision approximations of W to the K for all K. And those low precision estimates of W to the K for all K are going to come from the de-randomized square of graphs. And but in order to analyze it, though, even though we're using this de-randomized square of graphs, which is sort of a previously known algorithm, we're going to have to use a new notion of approximation called unit circle approximation, which we'll talk about some later in the talk. OK, so first, we're going to talk about how to get a high precision estimate of W to the K from a high precision estimate of L pseudo inverse. OK, so again, our goal is to approximate the entry of W to the, here we'll say K minus 1 to within a factor of plus or minus epsilon. And so let's say that W is this matrix that, or sorry, this graph that we've written down. So what we're going to do is we're going to lift this graph to a higher number of dimensions. And there's sort of a natural way of doing this. So any directed graph, you can naturally transform into a bipartite graph where all of the edges are directed from the left bipartition to the right partition. And what you just do is you have, in each of the bipartitions, you have a vertex corresponding to each vertex in the original graph. And then you have an edge from vertex U in the left bipartition to vertex V in the right partition if there was edge UV in the original graph. And that is a natural way of taking any directed graph and turning it into a bipartite directed graph where all of the edges are directed from the left bipartition to the right bipartition. And then we can just stack these bipartite graphs on top of each other. And this gives us sort of a sequence of bipartite graphs. And now we've gone up many dimensions, 2 to the K dimensions, where K is the number of times we've stacked. Or sorry, K dimensions, where K is the number of times we've stacked. And we call this the path lifted graph. And so we can write down the matrix for this graph. And it's just the matrix where you take the walk matrix W of the, oh, I should mention everything we're going to talk about today. We're assuming that the graph is unweighted, or equivalently everything has weight 1, and that it is a regular graph, and that we've normalized things and so that the adjacency matrix of the graph is the walk matrix. And so if we write down the walk matrix of, or equivalently adjacency matrix of this path lifted graph, then it's just obtained by taking the walk matrix of the original graph and just sticking it under the diagonal like we've written here. And this is a pretty nice matrix. And so as you might expect, if we subtract, and it can be viewed as a tensor product, where you just tensor the walk matrix with the adjacency matrix of the path of length K. And so this is like a pretty nice matrix, like if you write it down. And as you might expect from nice matrices, like it has a nice inverse that you can actually just write down in a closed form, at least symbolically in terms of W. So what I mean by that is, so what we've written down here is the Laplacian matrix of the path lifted graph. So the diagonal matrix of degrees IKN minus the walk or adjacency matrix, PK tensor W. And we take that whole thing and invert it. And this is going to give you an expression for the inverse of the Laplacian matrix. Since the inside is the Laplacian matrix, the inverse is the inverse of the Laplacian matrix. And it's a nice matrix, so you can write down the solution to this in closed form, it turns out. And when you do that, this is what you get. So if you look, we have the identity matrix tiled on the diagonal. And then immediately under the diagonal, we have W matrices. And then 2 lines under the diagonal, we have W squared. 3 lines under the diagonal, we have W cubed, and so on. And if you go all the way down to the bottom left corner, then we have a W to the K minus 1 in the left corner. So we can just read that off the bottom left corner. So what this says is that if you can exactly write down the inverse of this path of the Laplacian of this path lifted graph, then you can actually just read off W to the K minus 1 for the original graph. So this is an exact reduction. And of course, what this means is that, if you can write down this matrix, only approximately, but to high precision instead of exactly, then of course you can read off a high precision approximate W to the K minus 1. Now, of course, we've said that, in this talk, we're only going to be able to do things for Eulerian graphs. And, if you look, this path lifted graph, it's not an Eulerian graph. So how do we fix that problem? So what we can do is we can just add an additional vertex v, and that connects the first and last layer like so. So here we have vertex v. We connect the last layer to vertex v, and then connect v to the first layer. And we call that graph w hat. And then if you want to compute, what is the transition probability from s to t in the original w to the k, so this is the non-lifted, w, then we can just compute escape probabilities on this graph w hat. So what you just do is you would just compute, the probability that if we want, w, like the transition probability from s to t and w to the k, you would just compute instead the probability that a random walk from s to t, or sorry, a random walk visits s, a random walk starting from s visits t before it gets to v in this graph w hat, which is something that you can compute by solving a Laplacian system where the graph is w hat. And this is, of course, this graph is going to be polynomially larger potentially than the original graph, but because we're in a low space setting, that's actually fine, as long as it's only polynomially larger, not more than that. Yes. Okay, so that's how we take a high precision estimate of L pseudo inverse and turn that into a high precision estimate of w to the k. Now we're going to talk about how we take a low precision approximation of L pseudo inverse and boost it to a high precision estimate using preconditioned Richardson iteration. So suppose that we have some approximation to L pseudo inverse such that the norm of I minus L pseudo inverse tilde, that's the approximation, times L is smallish, meaning some fraction alpha that's less than a half. So if this looks familiar, it should, because it's the notion of approximation that we used when we analyzed preconditioned Richardson iteration in the last talk. So then what we can do is we can write we can expand L pseudo inverse as a sum where each term in the sum has the power of this I minus L pseudo inverse tilde times L in it times L pseudo inverse tilde.
Do you take the I here to be on the does I act only on the complement to the kernel of L?
So yeah, so we're sort of ignoring the kernel because I guess I didn't mention this, but for Eulerian graphs, just like undirected graphs, the kernel of a Laplacian matrix, assuming the graph is connected, is just the all ones vector. So we're just sort of assuming everything we're doing is orthogonal to the all ones vector. Here it doesn't quite matter like whether you think of I as being orthogonal to the kernel or not, though, because you have like a factor of L pseudo inverse tilde on the outside, which is going to force, like, it's going to kill the kernel of I anyway. Okay, so so the nice thing about this is that this expansion for L pseudo inverse in terms of L tilde pseudo inverse, right? If like each of these like the left factor in each of these terms that's being raised to the jth power, right? We said, right, that its magnitude in norm, right, is like less than a half, which means that as j goes to like infinity, like this this factor is sort of in size, right, going to be exponentially like decay to 0, which means that like the terms in the sum for large values of j are going to contribute a negligible amount. And so we only need to actually compute out log n over epsilon of these terms, because after that they're computing less than, or sorry, contributing less than like epsilon over n or something like that to the sum, like in total. And so ignoring them does not change the sum by very much entry-wise. So if we look at the amount of space that this algorithm uses, it's log n times log k. And the reason for that is just because it's a polynomial in matrices. And if you just do a divide and conquer, a standard divide and conquer algorithm, for that you can use for multiplying and adding things in low space, you get log n times log k. And here, right, we said that k was log n over epsilon, so this is log n times log n over epsilon. So this is nearly logarithmic space. And so that's how we get a high precision estimate of L pseudo inverse from a low precision estimate of L pseudo inverse using preconditioned Richardson iteration. Okay, now I'm going to talk about how we get that low precision estimate of L pseudo inverse from a low precision estimate of W to the k for all k. Or sorry. I think we're skipping that, right? Due to time. Yeah, we're skipping that actually due to time, but it uses ideas actually that are very similar to the ideas we talked about in the low time setting. And so what we're going to end the talk with then is how to get a low precision approximation to W to the k for all k from the de-randomized square of graphs, and how sort of this notion of unit circle approximation plays into it. Okay, so unit circle approximation is a definition of approximation for the Laplacian matrices of directed graphs. And it has the following key features. So suppose, we have a Laplacian I minus W tilde that approximates the Laplacian I minus W. Then what unit circle approximation requires is that if we raise the walk matrix to some power, there are Laplacian matrices still approximate each other. So I minus W tilde to the k still approximates I minus W to the k, even though we've powered the graphs, which is not a feature that like some of the ordinary notions of approximation that we've talked about actually have. And in particular, it does it with no change in the approximation quality. So you're not losing anything in like your epsilons. And so we're going to sort of motivate this by some scalar intuition. So we have a matrix I minus W, and we're going to think of that now just as a number 1 minus W instead, where W you should think of as like a either like a positive or maybe even a complex number. But for now, let's just say a positive number. And so if we have multiplicative approximation for positive numbers, right, just says that, if we have positive numbers A and B, they 1 plus or minus epsilon approximate each other if, their ratio is within a factor of 1 minus epsilon and 1 plus epsilon. And then you can ask, I said earlier that ordinary notions of approximation don't have this key feature that we want. And so we can sort of see this by saying, all right, does the multiplicative approximation, even for complex numbers, have this feature that, if we have, 1 minus little w now, tilde, and 1 minus w, and these things multiplicatively approximate each other, and now we raise w tilde to some power, do they still approximate each other? So does, for example, 1 minus w tilde squared still approximate 1 minus w squared with no loss in the approximation quality? And what you can show if you analyze this, it's just numbers, so it's just something you can analyze by just writing things down, is that even though, even if they approximated each other within, a 1 plus or minus epsilon factor initially, when you square them, now they might only approximate each other within a 1 plus or minus 2 epsilon factor. So you're losing, a constant factor potentially in the approximation error when you do this. And so what unit circle approximation for positive numbers does is it sort of, it's a stronger notion of approximation that prevents this kind of error blow up from happening. And so specifically for positive, so the sort of special case of unit circle approximation for positive numbers is it requires that 1 minus z w tilde and 1 minus zw approximate each other for z equals plus or minus 1. So in other words, 1 minus w tilde and 1 minus w need to approximate each other, and 1 plus w tilde and 1 plus w need to approximate each other, respectively. And what you can show is that, if you define approximation with this stronger, under the stronger notion, then you don't lose anything. Then you don't lose anything when you take powers of things. And so what unit circle approximation does is it generalizes this definition we've given here that was just for positive numbers to complex numbers in the non-symmetric matrices. And it's essentially in the way that you think if you go back to part 2 of the talk. So right, in part 2 of the talk, we defined a notion of approximation for non-symmetric matrices, a multiplicative approximation for non-symmetric matrices, between I minus W and I minus W tilde. And so now we just require that these non-symmetric matrices approximate each other, not not just I minus W and I minus W tilde, but I minus ZW and I minus ZW tilde for all Z on the unit circle.
So when you generalize to matrices, do you do it different phase shift for every possible eigenvalue, or you do just one phase shift of the unit circle for the whole matrix?
So we require the approximation to hold for all values of Z on the unit circle.
I see. So you use a definition of the matrix times the vector, and then you compare the vectors.
So actually, it's just it's just I minus ZW has to approximate I minus ZW tilde for all complex Z on the unit circle, where W here now is a matrix rather than a vector.
I see.
And then it's the strong, and it's the
remains scalar even though
what?
Z remains scalar even when you move to matrices.
Yes, that's right. Z remains scalar.
Okay.
Yeah, and so that's sort of how unit circle approximation works, at least at a high level. So now I'm just going to mention a couple of sort of open questions that are related to the things I've been talking about today. So sort of from a mathematical perspective, you could ask, some very interesting questions, I think, about directed Laplacian matrices. For example, is there a nice geometric interpretation for directed Laplacian matrices, sort of analogous to, in the undirected setting? I mentioned briefly that undirected Laplacian matrices, they're a discretization of the Laplace operator. So you could ask sort of, is there some nice differential calculus geometric interpretation of what's going on in the directed setting? Another interesting question I think you could ask is, is there a way of viewing arbitrary directed Laplacian matrices as undirected, or maybe even just, viewing Eulerian directed Laplacian matrices as undirected? That I think would be very interesting. And in particular, if you could do it for Eulerian Laplacian matrices, then it would sort of formalize the intuition that Eulerian graphs behave in a lot of ways like undirected graphs, but we don't know how to do that. And then finally, I think it'd be nice to get a better understanding of some of these notions of matrix approximation that we use for asymmetric matrices. From a computer science perspective, obviously, you would want to prove that RL is equal to or nearly equal to L. That'd be nice. Another thing that would be nice is, we can estimate with our work high powers of W to the K to high precision for Eulerian graphs in nearly logarithmic space. And you could ask, can you do this instead of in nearly logarithmic space in nearly linear time, and maybe even use the reductions that we have to the Eulerian case to get this to work not just for in the low time setting, not just for Eulerian graphs, but for all graphs. So that's like an interesting question, I think. And then finally, in the time setting now, could we use the directed Laplacian solvers that we have that run in nearly linear time to try to get faster algorithms for combinatorial problems? And another problem, which is maybe slightly less interesting, is a lot of these things have fairly nasty polylogarithmic factors, especially in the low time setting. I think there might be more than 10 logs on some of the nearly linear time algorithms for these problems. So it'd be nice, to try to shave some of these polylog factors too. And so that's the end of the talk. I'm happy to open it up to questions.
Yeah, thanks, John. That was great. And questions to John? I have questions, but I'm trying to get. Yeah. So anyway, here's one question. I mean, what do you think is really the major roadblock to get RL really close to L? I mean, just you do it for Eulerian and the generalization for fast mixing graphs like RTV. What if I just have a graph that's almost Eulerian, it just deviates by one edge from being Eulerian. How bad does it throw off your algorithms?
So one edge may not be a problem, but like a logarithmic number of edges might be a problem, because the problem is like that sort of deviations from Eulerianness can multiply. So if you have like a factor of like 2 deviation, like in several different places, then it may like be like a factor of, like if it's in like, if you have like, k deviations, you may end up like paying like a 2 to the k factor in like how badly it's messed up your stationary distribution. In terms of like the main barriers to RL versus L, like the algorithms do pretty heavily rely on the fact that the graph is Eulerian. And so like even in the low time setting, and sort of, the reason why we're able to solve non-Eulerian things in the low time setting is that we have a reduction to the Eulerian case. So figuring out some way of either making that reduction work in the Eulerian case or more directly solving the non-Eulerian case, I think is sort of what you maybe need to do. But unfortunately, like sort of if you try to naively make the reductions work in low time, they seem to like really want to take log squared space, or worse potentially.
Okay. I have more questions, but maybe I'll ask you separately. So any other questions to John? Going once, going twice. Okay. Thanks, John. And yeah, thanks all.